going to get started here. Nice to see everyone. Thanks for coming. It's the last session before closing remarks. I'm so excited you guys are here. And we have 4 amazing speakers on tap for tonight, for this afternoon. First, we have Megan Ayers, PhD candidate at Yale University. Next, we'll have Emil Cherrington, research scientist at NASA SERVIR and the University of Alabama at Huntsville. Then Alvaro Moreno of University of Valencia, Spain, and Nathaniel Robinson, the Nature Conservancy in the US. And the 2 of them are going to be talking about work that they've done with their colleague, Emma, oh goodness, I didn't practice Emma's last name, Izquierdo Verdigliar. I'm so sorry. What is it? Verdigliar. Thank you. And then at last, we'll have Liza Goldberg, biospheric scientist at NASA and Stanford University. So first up, we have Megan Ayers. Come on up, Megan. Let's welcome her.
Hi, everyone. I'm really excited to be here to talk with you about carbon leakage from carbon offset projects and our plans to assess it using a combination of experimental methods and satellite-derived measures of forest outcomes. So just to start, I'm going to give a quick intro example to carbon offsets and how they work. So I'm going to use Disney as an example of a big company that does take part in the voluntary carbon market. So you can imagine that Disney and a lot of other companies are producing emissions beyond some climate targets that they have. And to compensate for some of those extra emissions, they purchase these carbon offset units. And you can think of these units as a kind of waiver to excuse some of those extra emissions. And that's because the funding that Disney or other companies are providing to purchase these offsets is going in the form of credits towards projects elsewhere in the world that are working to prevent emissions or sequester carbon. We're focused on projects that do forest-based projects. And the central idea is that these decreases in emissions that are caused by the projects and funded by these companies are then canceling out the emissions of Disney in this example. And this voluntary carbon market of transactions like this has been growing in recent years, and it's been estimated to become as large as $250 billion by 2050. So it's becoming an important part in how emitters are voluntarily taking climate action. But I'm going to zoom away from the big picture into high level of how we calculate individual offsets with an example. So this is an imaginary avoided deforestation project area. We may be credited this project to not cut down trees here, and this is the amount of forest that we could observe after the project is over. And so we want to talk about how much carbon was offset by this project or how much deforestation was avoided. We're really making a comparison to a counterfactual scenario, right? So we might think that if we hadn't funded this project with the carbon credits, that a lot of forest would have been cut down and maybe we would see this top image. And if that's the case, then the credit had a really good positive impact. We would say that it's additional and doing what it's supposed to do. It's also possible that no deforestation would have happened and that we would see the same amount of trees cut down whether or not we awarded this carbon credit. And we don't know which of these actually would occur, right? Because we live in the world where we did enter into a carbon offset agreement with this land, and we have to make an educated guess about what would have happened if we hadn't. I think we all know at this point that good guesses and estimates about counterfactual scenarios and baselines requires good data, which is where Google Earth Engine comes in and provides a ton of remotely sensed outcomes of forests, along with other geospatial data that's really useful for this kind of work. And for one, that is used in some cases for individual projects and monitoring and verifying those projects, but it's also really central for wider scale evaluations of carbon offsets as a larger intervention across time and many different projects. And a lot of important work is focusing on doing evaluations like that and looking specifically at this question of how we estimate counterfactual scenarios to calculate offsets and whether or not those baselines are accurate. And that's really important work. But even if that's a really positive finding and all projects are additional and baselines are always estimated correctly, we could still have this problem that is frequently really overlooked, and that is carbon leakage. So I'm going to give a really simplified example of carbon leakage, but you can imagine that you have some piece of land, A here, and that if we did nothing and didn't protect it, we would lose half of the trees there. On the other hand, if we fund with a carbon credit to conserve this land, we could avoid deforestation from happening in land A, but we're not inherently changing the market demand for those wood products or that land. So maybe then the deforestation just shifts next door to land B, which is still unprotected. So that would be carbon leakage. And if this kind of thing is really rampant, then it's a big problem because we're excusing the ongoing emissions of the buyers who are funding these projects. And meanwhile, emissions are actually increasing outside of the project boundaries. And carbon protocols, which standardize how offsets are implemented and calculated in practice, they know that this is a big problem, but lacking any real empirical evidence about carbon leakage, most of them just implement a fixed leakage deduction from the credits that are awarded to projects, which is not an ideal solution, but because there's no rigorous investigation on the extent of leakage or what structures work to prevent it, they really don't have a choice, which is what we would like to change. So we are proposing the first really focused empirical study of leakage in these projects to better measure the extent of leakage and understand its structure. And I'm going to talk about how we're proposing to do that with a randomized control trial. Before I get into that, I'm just going to give a kind of higher level conceptual of how we're visualizing, evaluating leakage. So this is a simulated image of forested area. It's broken into pixels, and you can imagine pulling forest cover information or biomass or something from Earth Engine, and that's in green. We have presence of roads in gray, and then maybe we have 4 avoided deforestation projects in these blue circles that are in the carbon offset agreements, and they're receiving credits for not cutting down their trees. And so maybe we would wait until the projects are over and observe how much deforestation has happened in red here. And so the question we'd want to answer from this data is how much of this deforestation is just business as usual in the area and would just occur no matter what we did, and how much is leakage effects, how much is happening because we prevented it from happening in the blue circles and it just moved outside into the unprotected areas. And it's really difficult to separate those two kinds of deforestation if you don't have a carefully designed study, which is why we're proposing approaching this experimentally using a randomized control trial. So RCTs are the gold standard for estimating the kind of causal effects that we're implicitly talking about. And that's because by randomizing an intervention, so in this case by randomizing amongst these 8 units, acceptance into a carbon offset agreement, then we can be sure that the projects that do get credited are not systematically any different from the projects that don't get credited. And that allows us to compare the outcomes in the 2 groups and attribute any difference in their deforestation levels to the fact that some of them received these carbon offset agreements. Otherwise, we might be worried about things like adverse selection or confounding variables. And so in this case, when I was talking about baselines, here we can use the uncredited control units to give us that baseline, right, instead of guessing individually for every project. And so things are a little bit different when our projects affect each other. So in this case, when we think leakage is happening, it's possible that by entering a carbon offset agreement with one project, that actually does still have an effect on the eligible projects that don't enter into agreement. But we can extend the same kind of idea if we make assumptions about the structure of leakage. So for example, if we think leakage is very local and only happens very close to the credited projects, then we can compare the unprotected land that is close to the randomly credited projects with the unprotected land that is close to the randomly uncredited but eligible projects and look for differences in their outcomes. And that's a bit of a simplified example of what we think the structure of leakage looks like, but for more complex leakage effects, we can extend more recent methodological advancements in statistics with causal inference to do some more complex estimation of these effects. And so with those methods and with a designed study like this, we can test for different forms of leakage that we might expect to see and get a better idea of how prevalent that is. So I just have a few simulated examples of the kinds of leakage we might look for, using the same example of the credited and the uncredited projects, and now the red indicates leakage effects specifically. So this first image is what I was talking about, this proximity leakage, where leakage only occurs in a band right around the credited projects. This is what most evaluations and existing protocols look for, but we think probably that leakage effects are not spatially symmetric, so accessibility matters a lot in driving deforestation, so it's possible that leakage effects would be more concentrated in more accessible areas close to roads. You can imagine the same thing with proximity to timber mills and other spatial variables. It's also the case, or could be the case, that leakage has less to do with spatial proximity and more to do with the similarity. So maybe it's really important exactly what factors of land ownership and ecological factors were going on in the project where we prevented deforestation. And if that's the case, then we might expect to see more leakage effects in our projects that were eligible but did not receive credits, because by design they are on average exactly the same as the areas that did receive the carbon offset agreements. We could also find a combination of all of these structures of leakage, and we can probably brainstorm many more, but the central idea is that with this design, of this randomized design, we can test for different structures and have a better understanding of which are prevalent, the magnitude of leakage along those structures to inform future protocols and evaluations. Okay, so I'm just going to wrap up with some takeaways. So first, we do believe carbon crediting can have a valuable role in nature-based climate solutions, but we really need to understand the magnitude of carbon leakage and how much it is undermining the positive benefits of carbon credits. We can do that with a randomized study of carbon credits to better understand leakage and its structure. And finally, I want to plug that this is early work and that we are seeking partnership with interested stakeholders. So if you are interested in talking more about leakage and evaluating it with the randomized control trial, please reach out. We would love to hear from you. Here's my contact information and that of the 2 Yale faculty that I work with. Thank you.
Thank you so much, Megan. All right, next up we have Emil Cherrington, who's going to take my path as well. Okay, you're going to. No, it's fine. You caught me off guard there. No, it's great. So take it away.
Yeah, first off, thank you so much, Karen, for the invitation to present a little bit on some of the work that we've been doing in the SERVIR program. As it shows there on my slide, we do have, this work is in collaboration with a number of other folks who couldn't be here. That all said, just to talk a little bit about what we do. So first off, for some of you who might have missed our earlier SERVIR session on Tuesday, SERVIR is a partnership between the U.S. Agency for International Development, NASA, and leading centers in different parts of the world. As you can kind of see, if I can get the pointer to go, basically the map, there on the bottom, highlighting the areas in Asia, Africa, and Latin America that we're working. And basically, one of the things that SERVIR is a capacity building program, and one of the things about SERVIR is we like to think that we're connecting science and data with end users. With the work that we're doing with the carbon pilot, which is only a few years old, we'd like to think that we're essentially kind of also, building a bridge or going across from just land cover and land cover change data sets into now estimates of forest carbon stocks and greenhouse gas emissions. And to say that, traditionally in the almost 20 years that the SERVIR program has been around, the hubs that we work with in their different focus regions, they've done quite a lot of work in the areas of land cover change, land cover mapping, but going from, again, land cover into what the emissions are, what the stocks are, that is, something that they haven't done quite a lot on so far. That all said, overall for our SERVIR carbon pilot, or SCAP, the things that we're interested in knowing, just I guess at a research basis, but again with a focus on capacity building, is this idea of, in any given area of interest, what's the forest cover? What is the forest cover change? What are the stocks? And of course, based on the change, what have been the emissions? And long story short, we're using, heavily leveraging the different data sets that are already in Earth Engine to answer these questions, again, in coordination with with our partners in the different regions. For this pilot activity specifically, we have 15 countries that we're focusing on, again, in these different focus areas where we're working. But some of the stuff I'll present really briefly does touch on, other parts of the world. Part of, you might be interested in, the title of the presentation said ensembles. What do you mean by that? And so it's just the general idea of, we're running Earth Engine at scale and kind of crunching different data sets. We're making combinations of, again, global land cover maps, global change data sets, including ones that you've seen in other presentations before, combining those with spatially explicit biomass estimates at the global and pantropical level, and then from that extracting out estimates of what are the current forest stocks, and also how have changes in forest stocks contributed to greenhouse gas emissions, specifically from deforestation. And so, again, don't have, I guess, all the time in the world to kind of go into all of the details of what we've been working on. But, one of the things that we've done, again, at scale in Earth Engine is looking at, for instance, for the year 2020, there are actually 7 global land cover products, and from those we extracted just forest cover, for instance, from Dynamic World, from World Cover, from the Esri Land Cover, Global Forest Watch, MODIS, ESA, CCI Land Cover, et cetera. And what we can see, and again, probably the pointer's not working the best, but what we're seeing, for instance, in the red areas are where all of these different global products line up, where they all say, this is tree cover. And then, of course, in the areas in blue, where you'd see where, only one of the different 7 data sets say, this is tree cover. And so, just in terms of the ensemble approach and kind of understanding kind of what it all means. Because again, end users, there are all these different products out there, and their big thing is, what does it all mean? And so we can do similar kind of approach now, looking at the different biomass data sets that are out there. And in this case, we're looking at data for the year 2000, for which there are 11 different sources. Some of the ones that you're familiar with, for instance, Sasan Sachi's product, the one from Woodwell Climate Center, Bacchini et al., et cetera, et cetera. And if you take those and look at all of them in detail, of course, you're going to get a mean map. You're going to say, okay, what does that say? But now if we extract something like the coefficient of variation, in the blue areas, we're basically seeing where these 11 different forest carbon models, as it were, are lining up. And in other areas, like in the reds, is where you're seeing that they're not lining up. And so, for instance, what's interesting is, particularly in the tropics, the different forest carbon models are all saying, high areas of biomass, but it's actually in other parts of the world, for instance, in Cerrado in Brazil, or in East Africa, some parts of Mexico, and even, I guess, not so close agreement in the temperate and boreal zones. That's where these different products are saying they don't necessarily line up. And just starting to wrap up in terms of some of the work that we've been doing with Earth Engine specifically along those lines. You can also take that data and visualize it in a different way. Have to say, of course, that the idea of visualizing things along, for instance, the latitudinal gradient, this is work that Santoro et al. From ESA, the European Space Agency. This is work that he had originally started doing with fewer data sets, but essentially we lined up 16 models of biomass for the tropics as well as the globe. And you can see in the green line, the green thick line, where they all line up, and in the other areas where they're not lining up. So for instance, if we look at the area around the latitudes like, say, Chile and Argentina, that's where you have a number of carbon models which are essentially really in disagreement. And basically around the middle in the tropics, that's where you actually see, again, these different models are agreeing. And so, again, that's, in a nutshell, some of the stuff that we're doing. And then just kind of following off of some of the earlier presentations, and you saw in the previous session that Karen chaired, the work that, for instance, Silva Carbon is also doing in the capacity development sphere. Earlier this year, we partnered, for instance, with Silva Carbon and doing a training workshop in Guatemala, again, taking these techniques of not just looking at land cover, but when you have land cover and land cover change products, what does that mean in terms of emissions, et cetera? And so that's work we've done there, as well as in other SERVIR hubs. And in this room, we also have representatives of the other hubs in, again, other parts of Latin America, Asia, and upcoming next week, we're going to do a similar training like this in Belize, and next month in West Africa. And closing up with just some takeaways, some of the work that we're doing. Well, first off, in the NASA world, there's a big push for having everything be in open science and for it to be transparent. There's a NASA initiative right now called TOPS, Transform to Open Science. And so the work that we're doing, facilitated again by Earth Engine, is being done in a transparent way. I didn't quite get into, I guess, the full details of how the ensemble is working and the emissions estimates that we're also doing. But as you can kind of see from some of the stuff that we've shown, getting better ideas of where the uncertainties are, what the magnitude of the uncertainties are, and of course the capacity building stuff that I showed in the previous slide. And then we also have we have an economist on staff now looking also in terms of, okay, there are uncertainties. What does that mean in terms of money that countries could potentially get or not get? And then, of course, kind of showed in or highlighted in that app, we're also building a web platform, again, leveraging Earth Engine to put all this stuff up there. And with that, I'd just like to say thank you to everybody. And of course, thank you to my collaborators on this. So thank you.
Thank you so much, Emil. And I remembered what I was going to say last time, which was we're going to hold questions until the end, and then we'll get all the speakers up here and take questions together. All right. With that, I'll welcome Alvaro Marina Martinez and Nathaniel Robinson from University of Valencia and Nature Conservancy.
Hi. Thank you, Karin, for the nice introduction and for letting us talk a little bit about our work estimating carbon fluxes with Google Earth Engine. My name is Álvaro Moreno from the University of Valencia. And
I'm Nathaniel Robinson from the Nature Conservancy, Africa Business Unit. In 2017, the Nature Conservancy came out with a study that essentially said that nature-based solutions can provide about 1/3 of the total climate mitigation solutions necessary for keeping our goals for 2030. And nature-based solutions can come from sort of three main avenues: protecting intact lands that are significant carbon sinks, managing working lands that the management can increase the carbon storage capacity, and restoring degraded lands back to their capacity to hold carbon. The challenge is it's really difficult to measure that carbon increasing across these lands.
so it's very important to have these estimates in order to validate these policies and changes that nature-based solutions can provide. But the best estimate we have so far are the data provided by eddy covariance flux towers, but they are very costly to maintain and to provide due to all the costs of maintaining them in terms of economy and data of the sensors on the maintenance. And because of that, we only have sparse locations of these flux towers. And despite huge efforts in order to provide data worldwide, we don't have continuous observations of these carbon fluxes. So we need to figure out a way to produce maps with this data. And because we need to use that to validate these policies I was mentioned before. So how are we going to do that? Well, luckily for us, we have Google Earth Engine. We provide not only massive amounts of data, but also the computational power to process this data. So for example, from a remote sensing perspective, we can compute key variables of which are totally relevant to compute photosynthesis, the photosynthesis of vegetation. So for example, with vegetation indices like the NDVI, we can calculate the amount of chlorophyll we have in a given pixel, or more sophisticated biophysical parameters like the leaf area index will give us information about how many layers of vegetation we have. Or even with the FEPAR, we can know how much of this radiation is being captured by the vegetation itself. Or because we have so many observations in space and time, we can monitor the changes in vegetation health. Or if we use, for example, microwave data, we can even compute soil moisture or even soil irradiation over very large areas. Here I'm showing a couple of examples of some work we have done. For example, in the upper part of the figure, we can see the leaf area index we have computed using Google Earth Engine at 30-meter resolution continuously over Europe. And in the lower part of the figure, I'm showing an example of how we can have a lot of spatial detail in terms of solar irradiation, which is also obviously key for the photosynthetic process. So we know that we have this good reference data that's provided by Flux tower data, but we need to create models in order to use this remote sensing data and meteorological data to produce continuous maps at the scale in order to be able to assess these kind of nature-based solutions we were providing. And basically, there are three types of approaches to do that. The first one is based on data-driven methods, which is basically pure machine learning or deep learning approaches, which basically takes all the amount of data we have for the Flux tower or all these covariates we have with remote sensing and meteorological data, and they provide estimates in space. But the problem is that they require a lot of data, and the benefit is that they don't require prior knowledge about the photosynthetic mechanisms or processes that are being done by the plant itself. On the other hand, we have the mechanistic approaches, which are very complex models. We have most of the knowledge we have about how photosynthesis is carried out by plants. And as can be seen here, there is basically a combination of nested models and submodels, which basically represent all these processes. We have examples of this data, which is actually available in Earth Engine, which is Breathing Earth System Simulator. But the problem is that these kind of models usually require a lot of inputs. And the last type of models that we can find are the semi-empirical approaches, which kind of represent a sweet spot. So they are physically based, but they are easy to calibrate. And they are widely used mostly because of these two reasons. And also they scale very well over high computing resources because they are easy to compute. So one of the most well-known empirical approaches, I would say, to compute GPP is the algorithm implemented by NASA in the Mod 17 algorithm. As can be seen here, basically to compute GPP, we need to calculate the product of APAR and this epsilon of light use efficiency. The APAR is basically the amount of energy that we put into the system, which is the product of the FAPAR, which is a biophysical parameter I mentioned before, and the amount of PAR, which is the photosynthetically active radiation. It's basically 50% of the radiation in a given pixel. So APAR gives us an idea about how much energy we put into the system to capture CO2 from the atmosphere. But we have also this other parameter, the light use efficiency, which basically gives us the how the plant is basically converting this energy, which goes to the system, to capture CO2 due to the process of photosynthesis. But the problem is that plants don't function 100% all the time. So we add drone regulating factors that, for example, I'm showing here, like temperature, which takes into account that the photosynthetic process can be degraded due to extreme low temperatures, for example. Or I'm showing here another example of using BPD, which is a surrogate or a proxy of water stress that also obviously affects the photosynthetic process.
So the one thing we did was we took this Mod 17 algorithm. This was at the University of Montana for my PhD when I was a Brady Allred's student. Brady's now a Googler. With Matt Jones. And we basically ported that entire algorithm that NASA implements on the MODIS data set to work with Landsat. So you can see here an annual map of NPP, which is in kilograms of carbon per meter square per year. And we built that off of taking a very robust time series of Landsat data, converting sort of the Landsat available data from Landsat into FPAR and LAI, and then using the high-resolution meteorological data and land cover data to build out this model for the United States. And one of the biggest questions we get is, why do you stop at the edge of the United States? And that is a problem. We would like to be able to port these data sets more globally. And the algorithm, like we said, is implemented in Earth Engine. And as you can see, resolution on these data sets matter. So the original MODIS is on top. The satellite image from Google is in the middle. This is in the Bitterroot Valley of Montana. And the output from the Landsat-based model is on the bottom. And so in terms of being able to monitor nature-based solutions that often happen at a plot scale or a field scale or someone's property scale, we need to be able to take these models and implement them at higher resolution so we can capture those dynamics. And just to give you an example of that, this is a field in the TNC-owned property in northwest Montana, where they implemented some significant conservation agriculture practices. And the top right image shows the slope of NPP for the past 30 years. And as you can see, you can start measuring from the time you have a management intervention, a nature-based solution intervention, the difference in between a control area and the plot area, and then you can take the difference between that, and that sort of becomes your additional value of carbon. So that's what we are hoping to be able to produce more globally with the advent of things like dynamic world. So now we have access to land cover layers globally that are much more robust, that are updated, and well, in the case of dynamic world, every sentinel image. And then the couple pieces that are still sort of missing are very robust, high-resolution daily meteorological data sets. But the algorithm is there. We hope to start implementing it and bringing people's Flux tower data and other data to move these globally. The other piece of it is Alvaro and Emma have developed really, really robust ways of bringing the Landsat data and gap filling them and producing very clean time series. So, thank you.
Thank you.
Okay, at this time, can we have the rest of our speakers up here to the stage? And Emil, can you bring that mic with you? So you guys each get one. Okay, we have enough. I think. Okay, so if you have questions, there's a Q&A mic right there. I think that's best. Oh, and we have our friend here that can also bring you the. Are there any questions? There's one in the back there.
First, it's a comment for Emil about the forest lands in South America, especially in Chile and Argentina, where you mentioned the uncertainty. Did you cross your several classifications with the description of vegetation by local botanists to understand if the areas where you have that level of uncertainty, locally they're classifying that as forest or another type of ecosystem?
Yeah, that's a very good question, and thank you for the suggestion. Largely, we took, again, these 7 different global classifications for 2020, as well as 4 global classifications for the year 2000, and we basically just pulled out what they said was tree cover or forest cover, just based on, again, what those say. But it's a great suggestion in terms of moving forward, how those, I guess, cross-match with national systems, et cetera. For the 15 pilot countries that we're looking at, which unfortunately doesn't include Chile, but includes places like Guatemala, Costa Rica, et cetera, we have been pulling and using national maps and also then getting an idea of, okay, the different global products say this is tree cover or forest cover. What does the national product also say? Again, I just because of the interest of time, I didn't quite get to also show you kind of what the mix and match of matching the land cover data, the forest cover data with the biomass, what that looks like. But basically for any given area, we had, say for 2020, 7 forest cover maps, plus for 2020 we only have 3 global biomass products. But if you go back to 2000, then you have 11 biomass products times 4 global land cover products. And so of course then when you add in national products, you get an even bigger spread. And then of course when we're talking about the changes contributing to the emissions, we have then another, I guess, spread of land cover change data sets. But yeah, thank you.
I have another question, sorry, can I make it? It's for Nathan and Alvaro. One talk about GPP and the other talk about MPP. So if you can give a brief description. And also, you also talk about the use of land cover maps, and I didn't see in Alvaro's presentation how that was fitting the estimation of GPP. Thanks.
Good question. GPP and NPP are very highly related. If you subtract autotrophic respiration from GPP, you end up with NPP. So NPP is sort of probably the more applicable measure for trying to capture what is actually taken out and accumulated in plant tissue. So that would be the main difference there.
Yeah, in terms of the land cover used for the computation of the GPP or MPP, it plays a critical role because there is this maximum light use efficiency I mentioned, depends on the vegetation type, and other parameters in terms of the water stress and the thermal stress also depend on this land cover type. Usually, you have different parametrizations depending on the kind of vegetation you are considering in your semi-empirical approach. I don't know if that explains everything or. Time for the question.
Just following on the GPP and MPP, so the concept of epsilon in GPP, what is that accounting for? And what's the analogy for MPP?
So the first step is to calculate GPP, and the epsilon is the light use efficiency term. So it's the maximum, it's a physics-based approach where each plant type has a maximum capability of transforming light energy into mass. So that's where that term comes from. And once you calculate GPP, you essentially sum it up for an entire time period, and at the same time you have another component of the model which calculates respiration. And then you subtract respiration from that, and you can end up with NPP. So.
Right. Another question in here, and then I'll go up to the front after this.
Thanks for the great talks, everyone. This is for Megan. I didn't quite understand how the randomized control trial works. So the project areas aren't chosen at random at all. They're picked to be places that project developers think they can get good carbon outcomes from that. So could you explain a bit more about how that actually works and how you pick the other areas that you're testing against and stuff?
Yeah, absolutely. Yeah. So up until now, we don't randomize which projects enter into carbon crediting agreements. But what our project is proposing is that we find a pool of landowners who are willing to enter into some kind of lottery. So they are eligible for entering into these agreements to receive carbon credits. And yeah, the logistics would depend on our partners, and we need to figure some more things out. But the lottery is one idea of maybe we pay a base rate to all who are eligible and willing to enter, and then those who are randomly enter into the agreements are given additional financial compensation for avoiding deforestation. Other ideas are a delayed rollout, so we'd have a pool of eligible landowners. We randomly start the offset protocol early for some of them and wait a year or two or N years for the rest and induce some randomness that way.
Thanks, everyone. I had a question for Emil. If you had to partition uncertainty in your emissions estimates between the two things you're looking at, basically the activity data or land cover change and emission factors, how would you partition it, or what is your sense?
Yeah, let me I guess answer your question in a way that I'd like to. But I think part of it is just to say, in terms of the uncertainties between, say, the land cover data and the biomass data, it's much simpler for us to get a handle on, what's a better land cover product, right? Because, it's easy to collect, data, whether using something like Collect Earth Online, which is built on Earth Engine, and saying, okay, we know that, this global product, for instance, or this national product says this is a mangrove forest, or this is a pine forest, or a broadleaf forest, et cetera, right? We can tell whether it's wrong or right fairly easily. But the one where the uncertainty is really difficult to tell, it's the biomass products. Because, even in the calibration and the development of these different biomass products, they've used plot level data, mostly not LiDAR, or they're also, first off, they're not doing destructive sampling. And what does the literature say? Laura Duncanson from the JEDI team put together the CIAS biomass monitoring protocol. What does that say? The only real way for us to really know what the biomass is in a particular area is to cut it down and destroy it. The other ways of, let's do DBH, et cetera, that itself has an error on it. And so if we just use plots where we only have DBH, even that is essentially a model of what the biomass could be. And so my feeling, and I could be wrong, is that the uncertainties in the biomass data sets, and also as showed in the latitudinal graph, et cetera, you see where different models, some of them really disagree, or they disagree a lot in certain areas, versus I think where the forest cover, again, is something that it's much easier for us to, that land cover spot is wrong, et cetera, and we can figure out some way to fix it versus the biomass stuff. Again, it's hard to quantify by how much are the different models are wrong. And for instance, even if all the models agree for a specific area, that still doesn't tell us that that's the amount of biomass that's there, unless, again, we destructively sample it, or if you go again on the biomass protocol, it says there are other, LiDAR, like ALS-based metrics that then accurately estimate the volume. Kind of a long answer to your question, but yeah.
Thank you.
Hi, Tim Newman here from Earthblocks, and a lot of our customers are using Earthblocks to assess carbon projects for additionality and leakage and so on. So I was really interested, Megan, in what you're doing to sort of improve the ways we handle leakage. I was wondering whether you kind of talk about leakage as quite an abstract thing, but obviously it's people doing it, whether either you or others are sort of studying the motivations and the ability to travel and that sort of thing to inform where you might look and the kind of the patterns you might expect, as well as coming at it from a sort of more abstract point of view.
Sorry, can you repeat the question?
So I guess you're looking at leakage kind of statistically. Leakage is caused by people. Those people have ways of moving. They have different motivations. I was wondering whether you or others had looked at that and sort of tried to work out from a sort of human motivation point of view and a human ability to cause leakage, if that could help understand where to look and how far you have to cast the net and so on, as well as doing it kind of from the statistical point of view.
Like, if I understand your question, like how to understand, what is driving people to do this and how decisions they're making.
Exactly,
and
yeah.
How to find there. Yeah, and there's been some economic work as well, kind of looking at it from more of an economic perspective and modeling it that way, that we are aware of. I think the benefit of looking at it from the statistical perspective is there's different levels of structure that you have to or don't have to impose with stronger or weaker chances of detecting effects. But yeah, I think your point is a good one, and it's beneficial to think from those perspectives as well of, where we might expect to see leakage. But I think we've already begun thinking about that, and I think like accessibility is a big part of it that we know drives deforestation, and we'll continue looking into things like that.
Hi, thank you. I have a question for Emil. And I was just wondering, maybe kind of similar to what the gentleman was asking in the back about when the carbon models disagree at certain latitudes. If it's that same issue you see where it disagrees at different latitudes, or if it's all kind of the same. And so question number one is how you would harmonize that. And I guess as a follow-up question, number two, in the places where it is where they do agree, like at the equator, and I noticed at some other places, if that is related to biomass somehow. So if there's some way that there's more biomass, that would mean there's more agreement with the carbon modeling.
Yeah, thank you. And so I guess thank you for the question. Maybe just to clarify also, the graphic that I was showing based on that Earth Engine app, we're looking at forest biomass. So it is above ground biomass estimates, which of course we can fairly easily convert that to estimates of forest carbon. In terms of the distinctions, the differences, et cetera, there are multiple ways, I guess, to look at where they agree or disagree. Just comparing them by latitude was one way, but definitely if you look on a site-by-site basis, you're also going to see disagreements, et cetera. And the other map where I showed the coefficients of variation, I guess that was kind of like to show on a pixel-by-pixel level where, if you remember the colors in the blues is where they more or less converged, and in the reds is where they diverged. In terms of how to address how they're converging or diverging, I guess that's kind of one where we see it as not in our wheelhouse, where part of what we're doing is we're not trying to say, you know what, use this model or use that model, but merely to understand what all the models are saying, thinking that there's people with other areas of expertise who can probably do a much better job than we can in saying how to improve the different estimates.
Thank you. I think, if there's no more questions, we can finish 3 minutes early, or that's a really inspirational note to end on. But if there are more questions, we can stay in the nitty gritty and get scientific. What do you guys want to do? More questions? One more? Any final comments from our speakers? Questions for the audience as we walk out the door? Okay, I just want to say thank you guys so much. This was a really fun session, and I'm really happy we ended on it because I'm really feeling hopeful. Now we're going to go downstairs, eat our final snacks, and go together in the big room. So thank you so much. Thank you to the speakers. Thank you guys.